Have you ever stopped to think about where you really came from? I'm not talking about your hometown or the hospital where you were born, but about the true origin of the atoms that make up every cell in your body, every thought that passes through your mind, every beat of your heart. Neil deGrasse Tyson, one of the world's most respected astrophysicists, has an answer to this question that goes far beyond what your intuition could imagine. And when you understand what he discovered, your sense of who you are and your place in the cosmos will never be the same, because the scientific truth behind your existence is both more humbling and grander than any origin story you've ever heard. The answer is not just in your parents or your grandparents, nor even in the long evolutionary chain that goes back to the first single-celled organisms that appeared billions of years ago in the Earth's primitive oceans. The answer is written in the stars, literally. And to understand it, we need to take a journey through time that goes through not only the history of humanity or life on Earth, but the history of the universe itself since its first moments. And if you are one of those who love to unravel the deepest mysteries of our cosmic existence, subscribe to the channel because, together, we will explore scientific revelations that will completely transform the way you see yourself in the universe. When we look in the mirror in the morning, we see a familiar face, a person with a personal history, with memories and a unique identity. But physics reveals something extraordinary about this apparently simple image, because the atoms that make up your skin, your eyes, your brain, are not really yours in the sense we imagine. They are just temporary visitors in a body that keeps them organized for a few decades before returning them to the eternal cycle of cosmic matter. Every carbon atom that forms the structure of your organic molecules, every oxygen atom that you breathe right now, every iron atom that transports oxygen in your blood through hemoglobin, every calcium atom that gives rigidity to your bones, all these fundamental elements of the chemistry of life have a biography that goes back to unimaginable places and times. Neil deGrasse Tyson popularized one of the most poetic and accurate statements in modern astrophysics when he said that we are made of stardust. But that statement is not just a pretty metaphor to inspire awe for the cosmos. It is a verifiable scientific fact that reveals deep connections between nuclear physics, stellar evolution, and the very possibility of your existence right now by reading or hearing these words. To truly understand where you came from, we need to go back in time to a specific moment in cosmic history, approximately 380,000 years after the Big Bang, when the universe had expanded and cooled enough that electrons could finally bond with atomic nuclei and form the first stable neutral atoms, an event that physicists call recombination, although technically it should be called combination because it was the first time this happened. Before this moment, the universe was an incandescent plasma where photons of light constantly collided with charged particles, making the cosmos completely opaque, like trying to see through a wall of dense, luminous fog. But after recombination, the light was finally able to travel freely through space, and it is this ancient light that we detect today as the cosmic microwave background radiation, a kind of luminous echo of the birth of the universe. But here's something fascinating that Neil deGrasse Tyson often emphasizes in his lectures and books. At that primordial moment in the cosmos, only 3 chemical elements existed in significant quantities: hydrogen, which made up about 75% of all normal matter in the universe, helium, which made up about 25%, and tiny traces of lithium and beryllium. This means that for hundreds of millions of years after the Big Bang, the universe was chemically simple in a way that would make life absolutely impossible. Because life as we know it depends on much greater chemical diversity, needs carbon to form complex organic molecules, oxygen for aerobic respiration, nitrogen to build amino acids and proteins, phosphorus for DNA and RNA, sulfur for certain essential proteins, and dozens of other elements that simply did not exist in that early universe. So how did these elements come about? How did the universe go from a cosmic soup of just hydrogen and helium to the rich periodic table we know today with more than 90 natural elements? The answer lies in the stars, specifically in the process of stellar nucleosynthesis that takes place in the burning cores of these immense balls of gas that lights up the night. Imagine a gigantic cloud of hydrogen gas floating in empty space, with dimensions reaching hundreds of light-years in diameter, containing a mass equivalent to thousands or millions of times the mass of our Sun. This cloud was originally born from the leftovers of the Big Bang, composed almost exclusively of hydrogen and helium, but slowly, under the inevitable influence of gravity, it begins to collapse on itself. And as the cloud contracts, the density and temperature at its center progressively increase. When the core temperature reaches approximately 10 million degrees Celsius, something extraordinary happens. The hydrogen nuclei begin to move so quickly that they manage to overcome the natural electrical repulsion that exists between positively charged particles and fuse with each other, starting the process of nuclear fusion that defines a star. 4. Hydrogen nuclei combine through a series of reactions to form a helium nucleus, releasing energy in the process. And this energy is no small feat. It is so much energy that it creates an outward radiation pressure that exactly balances the force gravitational pull inward, keeping the star in a state of equilibrium that can last billions of years. Our own Sun is in this phase now, quietly converting 600 million tons of hydrogen into helium every second for approximately 4.6 billion years, and will continue to do so for another 5 billion years before its core hydrogen fuel runs out. But here is where the story gets truly interesting to understand its origin, because when a massive star, say over 8 times the mass of the Sun, runs out of its central hydrogen, it does not simply die. Instead, it enters a new phase of atomic creation. The helium core now contracts under its own weight until the temperature rises even further, reaching about 100 million degrees, hot enough for the helium nuclei to begin to fuse. 3 helium nuclei combine to form carbon through a process called triple alpha, and some carbon nuclei capture additional helium to form oxygen. Suddenly, the universe gained 2 new elements fundamental to life, and the star now has a core of carbon and oxygen surrounded by a layer where helium is still fusing, and another outer layer where hydrogen continues to burn. For really massive stars, the story doesn't end there. And this is where Neil deGrasse Tyson gets particularly excited when he explains to audiences why these cosmic giants become veritable element factories. As carbon and oxygen accumulate in the core, the temperature continues to rise, eventually reaching 600 million degrees, enough temperature to fuse carbon into heavier elements like neon and magnesium. Then at 1 billion degrees, the neon fuses. Then the oxygen at 2 billion degrees, forming silicon and sulfur. Each stage of fusion lasts less time than the previous one, because the heavier elements release less energy when fusing, and the nucleus needs to contract more quickly to keep the reactions happening. And I imagine you are realizing now that within these massive stars, all the chemical diversity necessary for rocky worlds and complex life is being built. But there is still a crucial part of the story missing, because nuclear fusion can only continue as far as iron. When the star finally starts fusing silicon into iron at temperatures of 3 billion degrees, it has reached a fundamental limit of nuclear physics. Iron has the most stable nuclear configuration of all the elements. Its binding energy per nucleon is maximum. This means that fusing iron into something heavier does not. It releases energy. It actually consumes energy. So when the star's core becomes a ball of pure iron with a mass comparable to that of our Sun, but compressed into a volume the size of Earth, nuclear reactions simply stop. And right now, you're wondering where the elements heavier than iron came from. like the copper in your veins, the zinc in your enzymes, the silver in your jewelry, the gold in your rings, the uranium in your nuclear power plants. And here's one of the most spectacular revelations of modern astrophysics that Tyson often emphasizes. These elements were forged in the most violent and energetic event a star can experience, a supernova. When the iron core of a massive star reaches critical mass, there is nothing left that can hold back the relentless force of gravity. In a fraction of a second, literally less than a second, the core collapses in on itself. And this collapse is so violent that electrons are forced into protons, forming neutrons and releasing a torrent of neutrinos. Matter reaches densities so extremes that a teaspoon of the core material would weigh millions of tons. And then, abruptly, the collapse stops when the matter reaches nuclear density, a density comparable to that of the atomic nucleus itself, creating something like a giant atomic nucleus the size of a city, called a neutron star. The falling material bounces off this incomprehensibly dense core, generating a shock wave that travels outward through the star's outer layers at a significant fraction of the speed of light. And as this shock wave passes through the element-rich stellar gases, it creates conditions of temperature and density so extreme that nuclear reactions impossible in any other context take place. Atomic nuclei are bombarded with free neutrons so quickly that elements heavier than iron are synthesized through the process called rapid ion capture. Neutrons, this is how gold, platinum, uranium, and all the heavy elements of the periodic table were born, forged literally in the last explosive breath of dying giant stars. The supernova then ejects all of these element-enriched outer layers into interstellar space at speeds of thousands of kilometers per second, creating an expanding nebula of colored gas and cosmic dust that spans tens or hundreds of light years, and this enriched dust eventually mixes with clouds of interstellar gas, clouds like the one we described before. But now these clouds are no longer just hydrogen and helium. They carry with them all the chemical heritage of previous generations of stars, carbon, oxygen, iron, silicon, and all the other elements that make rocky planets and life possible. And now, I'm curious, where are you watching this video right now? From Brazil, from Portugal, from some other corner of this blue planet that floats in the cosmos? Comment on your city or country, because it's incredible to think that no matter where you are in this world, the atoms that make up your body have followed the same epic journey through space and time. We all share this common cosmic origin that connects us not only to each other, but to every star that has ever shone. Aproximadamente 5 bilhões de anos atrás, uma dessas nuvens enriquecidas existia em um braço espiral da nossa galáxia, a Via Láctea, contendo não apenas hidrogênio e hélio, mas também todos os elementos pesados que gerações anteriores de supernovas haviam depositado naquela região do espaço ao longo de bilhões de anos, e algo perturbou essa nuvem, talvez a onda de choque de uma supernova próxima, talvez o encontro gravitacional com outra nuvem, mas, seja qual foi o gatilho, a nuvem começou a colapsar. E conforme colapsava, ela se fragmentava into smaller pieces, each destined to become an individual star or star system. One of these fragments, containing approximately a solar mass of material, began to spin faster and faster as it collapsed, because when something that is spinning shrinks, it spins faster to conserve angular momentum. It is the same principle that makes an ice skater spin faster when he pulls his arms closer to his body. And this collapsing and rotating fragment naturally flattened into a disk, with most of the mass being concentrated in the center where temperatures and pressures were rising rapidly, while in the outer regions of the disk, cooler temperatures allowed that particles of dust and ice would form. Microscopic grains of silicates, graphite, water ice, methane ice, each containing those precious heavy elements forged in ancient stars. At the center of this protoplanetary disk, the temperature and pressure finally reached the critical threshold for nuclear ignition, and a new star was born. Our sun began to shine 4.6 billion years ago, but what interests us particularly in understanding its origin is what happened in that disk of gas and dust that surrounded the young sun, because within that disk was all the raw material that would eventually become the planets of the solar system, including the Earth, including you. In the first few million years after the birth of the sun, those microscopic grains of dust in the disk began colliding with each other, sometimes sticking together due to electrostatic forces, like when you rub a balloon against your hair and it sticks to the wall. And through billions and billions of these collisions, the grains grew into pebbles, the pebbles into boulders, the boulders into asteroids, and the asteroids eventually into protoplanets, bodies with hundreds of kilometers in diameter, whose own gravity was already significant enough to begin attracting additional material more efficiently. In the region where Earth would eventually form, approximately 150 million kilometers from the Sun, the temperature was too hot for water ice, so planetesimals formed. The remaining ones were composed mainly of rocky and metallic materials, silicates like olivine and pyroxene, iron oxides, magnesium compounds, all built from the same heavy atoms that ancient stars had created and scattered throughout space. Through more collisions, some protoplanets grew faster than others, their increasing gravities allowing them to dominate their orbits, accumulating most of the available material in their vicinity. And through this violent and chaotic process that lasted tens of millions of years, Earth was born, not through a gentle, gradual process, but through cataclysmic impacts that melted the planet's entire surface repeatedly, each collision with a large protoplanet, releasing enough energy to vaporize rocks and create temporary oceans of magma that covered the entire world. One of these collisions was particularly dramatic and has direct consequences for its existence today. Approximately 50 million years after the beginning of the formation of the solar system, a Mars-sized protoplanet, which scientists call Theia, collided obliquely with the young Earth. The impact was so energetic that it vaporized and ejected a significant fraction of the mantle of both bodies, creating a ring of vaporized and molten rock orbiting around the Earth. And from this ring, in just a few thousand years, our moon condensed it, so every time you look at the moon in the night sky, you're seeing the direct result of one of the most violent events in our planet's history. And you're seeing material that was literally part of the ancient Earth before it was uprooted into space. But what is important to our origin story is that after this chaotic period of initial planetary formation, the Earth slowly began to stabilize. The surface finally cooled enough to allow the formation of a solid crust. Water vapor in the atmosphere condensed and fell as rain that lasted millions of years, forming the first oceans, and chemical elements began to segregate within the planet. Iron and nickel, being denser, sank to the center, creating Earth's metallic core, while lighter silicates floated upwards, forming the mantle and crust. This process of chemical differentiation was crucial because it created diverse geochemical environments where different minerals and compounds could form. And all those elements that make up your body today were present on the early Earth, carbon atoms that billions of years before had been forged inside red giants through the triple alpha process, oxygen atoms created in the same helium fusion, iron atoms born in the cores of massive stars just before they exploded, atoms of iodine, selenium, zinc, copper, all created in the last seconds of supernova life. Now these atoms were trapped in the rocky matrix of the young Earth, awaiting the geological and biological transformations that would eventually release them and incorporate them into life forms. During the first billion years after its formation, Earth continued to be bombarded by asteroids and comets, left over from the formation of the solar system, impacts that were simultaneously destructive and creative, because, while they certainly made the surface inhospitable, they also delivered important volatile materials such as additional water and simple organic compounds, carbon-containing molecules that had formed in the cold regions of the protoplanetary disk, or even earlier, in the interstellar medium. Gradually, conditions on the Earth's surface became less hostile, and at some point between 3.8 and 4.1 billion years ago, perhaps in some hot pool near hydrothermal vents on the ocean floor, or perhaps in shallow lagoons exposed to cycles of evaporation and concentration, simple organic molecules began to organize themselves into more complex structures. Amino acids linked together to form primitive proteins. Nucleotides linked together, creating the first RNA molecules capable of storing information and catalyze chemical reactions. Lipids formed membranes that could encapsulate these molecules, creating compartments protected from the external environment, and through processes that we still do not fully understand, but that are the subject of intense scientific research. Life emerged. The first molecular replicators capable of making copies of themselves began to compete for resources. And evolution by natural selection began its epic work of transformation. These early life forms were inconceivably simple compared to even the simplest modern bacteria, but they carried a revolutionary characteristic. They could reproduce and evolve, and in doing so, they began to transform not just themselves, but the planet itself. Because as life diversified and developed new metabolisms, organisms learned to extract energy from diverse chemical sources, and crucially, about 2.4 billion years ago, some microbes evolved the ability to carry out photosynthesis, using energy from sunlight to split water molecules and release oxygen as a byproduct. The gradual oxygenation of the Earth's atmosphere was one of the most dramatic transformations in the history of our planet. Because free oxygen is extremely reactive, it is a poison to many anaerobic life forms that dominated the early Earth, but it also opened up entirely new metabolic possibilities. Organisms that could use oxygen to burn nutrients gained much more energy than anaerobic metabolisms, allowing for greater complexity and larger sizes. And gradually, over billions of years, life evolved from simple cells to multicellular forms, developed tissues, specialized organs, nervous systems, brains capable of processing information and generating consciousness. And at each step of this incredible evolutionary journey, the same atoms forged in ancient stars were being recycled through living organisms. A carbon atom could spend millions of years trapped in limestone on the ocean floor, then be released by geological processes, absorbed by a plant through photosynthesis, consumed by a herbivorous animal, preyed upon by a carnivore, decomposed by bacteria after that carnivore's death, released back into the atmosphere, absorbed by another plant, and so on, in an endless cycle of transformation and recycling. Neil deGrasse Tyson often emphasizes this point when he talks about our connection to the cosmos. The atoms in your body are not permanent. You are constantly exchanging matter with the environment around you through breathing, eating, excretion. Every breath you take contains atoms that have been in thousands of other people, in animals, in plants, in oceans. Some of the nitrogen atoms in the proteins in your brain right now may have been in the brain of Albert Einstein or Marie Curie decades ago. Some of the oxygen atoms you just inhale may have been exhaled by a dinosaur 100 million years ago. This constant circulation of matter through the Earth's biosphere connects all life into a common material network that spans time. And now think for a moment about the implications of this scientific perspective. When you look at your hands, you are not really seeing yourself in some permanent sense. You are seeing a temporary configuration of atoms that are billions of years old. Atoms that once existed in countless other forms before temporarily arranging themselves into the specific pattern we call your body. The carbon in your DNA molecules, carrying all the genetic information that makes you you. Born in the heart of a red giant that lived and died long before the sun existed, the calcium that gives structure to your bones, allowing that you move through the world, was created in nuclear reactions that took place billions of degrees inside a massive star. The iron in your hemoglobin that is carrying oxygen to every cell in your body, right now as you hear or read these words, was forged in a stellar core just before that star exploded, as a supernova spreading its enriched elements into space. If you would like to explore more of these profound revelations about our connection with the universe, like this video and tell me in the comments which of these scientific discoveries most impacted your way of seeing reality, because the more we understand about physics and cosmology, the more extraordinary our existence reveals itself. But the story of your origin goes even further than what we have already discussed, because while the heavy atoms in your body came from stars that died before the sun was born, the most abundant atoms in you, hydrogen and oxygen, have an even more ancient and fundamental history. The hydrogen that makes up about 60% of the atoms in your body was not created in stars. It is even older than that. It is primordial matter from the Big Bang itself. When we look at the atomic composition of a typical human being, we discover something fascinating. In terms of number of atoms, not mass, about 61% of the atoms in your body are hydrogen, 26% are oxygen, 11% are carbon, 1.1% are nitrogen, and all the other elements together make up less than 1%. This means that the majority of the atoms that make up you, almost 2/3, are the simplest and oldest element in the universe, hydrogen, one single proton with a single electron. And these hydrogen atoms were not created in stars. They were created in the first 3 minutes after the Big Bang during a period called primordial nucleosynthesis. So let's go back to the absolute beginning of cosmic history. About 13.8 billion years ago, all of the space, time, matter, and energy that make up our observable universe existed in a state of unimaginable density and temperature. We don't know what caused the Big Bang or what existed before, if it even makes sense to talk about, before when time itself may have begun at that moment. But we know with extraordinary scientific confidence, based on multiple lines of observational evidence, what happened in the first moments after the expansion began. In the first second, the universe was so hot that not even protons and neutrons could exist, just a plasma of quarks, gluons, electrons, neutrinos, and photons. But as the universe expanded, it cooled, and when the temperature fell below 1 trillion degrees, quarks could finally combine to form protons and neutrons, the building blocks of all atomic nuclei that would exist from then on. Over the next 3 minutes, as the temperature dropped from 1 trillion to about 1 billion degrees, protons and neutrons collided and stuck together through the strong nuclear force, forming the first atomic nuclei, deuterium, a proton bound to a neutron, helium-3, 2 protons and a neutron, helium-4, 2 protons and 2 neutrons, and small amounts of lithium. But after about 3 minutes, the universe had expanded and cooled too much for these nuclear fusion reactions to continue, so primordial nucleosynthesis stopped, leaving the universe with approximately 75% hydrogen, 25% helium, and traces of other light elements. The hydrogen protons that did not fuse during those first few minutes simply remained as solitary protons, each eventually capturing an electron when the universe cooled sufficiently 380,000 years later. And these primordial hydrogen atoms still exist today, diluted throughout the cosmos, some embedded in stars, some floating in the interstellar medium, and some, through an extraordinary chain of cosmic, geological, and biological events, ended up embedded in you. So when you drink a glass of water, each H2O molecule contains 2 hydrogen atoms that are literally relics of the first 3 minutes of the universe, and 1 oxygen atom that was created billions of years later in the core of a massive star, that water in your glass is a mixture of different cosmic times. Elements born in completely different eras of universal history, now united temporarily in a simple molecule that sustains your life. Neil deGrasse Tyson often uses this perspective to remind us that we are simultaneously old and young in cosmic terms. The atoms that compose us are unimaginably old, but the specific configuration they form, the precise organization of trillions of atoms that creates a conscious human being capable of contemplating his own origin. This is extremely recent and transient. Your personal identity, your memories, your personality, this is all a pattern of information temporarily encoded in the physical organization of ancient atoms. When you die, the atoms do not disappear. They simply reorganize into other forms, returning to the eternal cycle of matter. This scientific understanding of our origin raises profound philosophical questions about identity and continuity. If the atoms in your body are constantly being replaced, if every 7 to 10 years virtually every atom in your body has been exchanged for other atoms through normal metabolism, then in what sense are you the same person you were a decade ago? The modern scientific answer is that your identity resides not in the specific atoms, but in the information. In the pattern of organization of those atoms, your brain maintains continuity of memory and personality, even as the physical atoms that compose it are gradually replaced. It is like a river that maintains its identity as a river even though the water flowing through it is constantly changing. The Amazon River is recognizable as the Amazon not because it contains the same water molecules, but because it maintains its flow pattern, its course, its structure, even when the substance that composes it constantly changes. Similarly, you are you not because you are made of a specific and permanent set of atoms, but because you maintain a pattern of organization and information that persists through time, even as the atoms that instantiate that pattern are exchanged. And that pattern has its own evolutionary and developmental history. Countries, in an unbroken chain that goes back through the entire history of life on Earth, through our primate ancestors, early mammals, ancient reptiles, amphibians, fish, to the first multicellular organisms, and finally, to those primitive molecular replicators that emerged billions of years ago. So your origin is truly multiple layers intertwined. There is the material origin, the very atoms that make up your body, which came from ancient stars and the Big Bang. There is the biological origin, the evolutionary lineage that connects you to all life that has ever existed on Earth through 3.8 billion years of evolution. There is the developmental origin, the process by which you grew from a single cell to a complex multicellular organism with trillions of specialized cells working in harmony. And there is the informational origin, the memories and experiences that form your consciousness and personal identity. Each of these layers of origin has its own timescale. The hydrogen atoms in you are almost 14 billion years old. The heavy atoms are a few billion to tens of billions of years old, depending on when the stars that created them lived and died. Your specific genes have histories that date back to different points in the evolution of life. Some genes are shared with all life forms and can be almost 4 billion years old. Others are specific to mammals and are hundreds of millions of years old. Still others are unique to humans and are only a few million years old, and your personal memories have obviously only existed for a few decades, at most. And if you're enjoying this deep exploration into the cosmic origins of our existence, share this video with a friend who is also fascinated by the mysteries of the universe, because this kind of scientific knowledge fundamentally changes our perspective on who we are and our place in the cosmos. But there is another dimension of your origin that Neil deGrasse Tyson often explores that is even more intriguing: the origin of the energy that sustains your life. Because life is not just the organization of matter, it is also a constant flow of energy. You need to eat to extract chemical energy from food. You need to breathe to use oxygen in the metabolic combustion of that energy. Your body is a machine that constantly transforms energy from one form to another, converting chemical energy into movement, into thought, into maintaining body temperature, into cellular repair and growth. Without this constant flow of energy, you would die in a matter of minutes or hours. So where does the energy that keeps you alive right now come from? If you trace the energy chain back, you ate foods that got their energy from plants, or from animals that ate plants, and plants got their energy through photosynthesis by capturing sunlight, then essentially all of the energy that flows through the Earth's biosphere, with a few exceptions in deep hydrothermal vents, comes originally from the sun. Every calorie you burn, every movement you make, every thought that passes through your brain is possible because 8 minutes ago, photons of light left the surface of the sun and traveled hundreds of miles, and 50 million kilometers through empty space until they reached Earth, where they were captured by chloroplasts in plant cells and converted into chemical energy stored in molecular bonds. But the story of energy goes beyond that, because where does the sun get its energy from? As we have already discussed, through the nuclear fusion of hydrogen into helium in its core, and this nuclear energy fundamentally comes from the conversion of mass to energy according to Einstein's famous equation E equals mc squared. A small fraction of the mass of the hydrogen nuclei being fused is converted into pure energy that eventually escapes from the sun as light. So when you eat a banana and get energy from it, you are literally consuming sunlight converted into organic matter. And that sunlight, in turn, is nuclear energy that was originally mass converted into energy in the nucleus of the sun, and that mass in turn came from the gravitational collapse of the primordial gas cloud that formed the sun 4.6 billion years ago. And that primordial gas came from the expansion and cooling of the Big Bang. So the energy flowing through you right now has a lineage that goes back to the very birth of the universe, passing through countless transformations. Radiation energy in the early universe converting to thermal energy converting to gravitational potential energy as matter collapsed into structures, gravitational energy converting to nuclear energy in stars, nuclear energy converting to light converting to chemical energy in plants, chemical energy being transferred through food chains to you, and at each step in that process, a fraction of the energy it's dissipated as heat increasing the entropy of the universe as predicted by the second law of thermodynamics. But a fraction is also captured and organized in increasingly complex ways, allowing the emergence of structures such as stars, planets, life, and consciousness. And this perspective reveals something profound about our place in the cosmos. Far from being separate from the universe, outside observers contemplating something alien, we are literally the universe becoming aware of itself. The atoms in your brain, forged in previous generations of stars, have organized themselves in such a way through biological evolution that they can now process information, form internal models of reality, and contemplate their own origin. When you look up at the stars in the night sky and feel awe at the immensity of the cosmos, it is ancient star atoms in your brain looking back at you, their places of birth. Neil deGrasse Tyson has a wonderful quote about this that perfectly captures this idea. He says that we are part of the universe that has gained consciousness, made of stardust gazing at the stars, atoms organized in such a way that they can think about atoms. And this is not just a poetic statement. It is an accurate scientific description of our situation. The organic chemistry that allows life is possible because stars synthesized heavy elements and distributed them throughout space. Biological complexity is possible because the Earth provided a stable environment for billions of years where evolution could operate. And the consciousness is possible because animal brains have evolved the ability to process information in increasingly sophisticated ways until reaching a threshold where self-awareness and abstract thought emerge. You are simultaneously insignificant and central to this cosmic story. Insignificant because you are a temporary organization of matter on a small planet, orbiting an ordinary star in a galaxy among billions. Your lifespan is a blink of an eye compared to the age of the universe. Central because it is through beings like you that the universe experiences itself. That information about the cosmos is processed and understood. That meaning and purpose, however subjective, are created. And if you have any questions or concerns about any aspect of this scientific journey we've charted from the Big Bang to your existence, leave them in the comments below because I love exploring these deep questions about physics, cosmology, and our place in the universe. This community of people fascinated by science is one of the most rewarding aspects of making these videos. When you really absorb this scientific understanding of your origin, it changes something fundamental in the way you experience everyday life. Suddenly, those mundane activities, eating, breathing, moving through the world, take on an added cosmic dimension. You are not just consuming food. You are participating in an ancient cycle of matter and energy transformation that connects you to the entire biosphere, and through it, to the sun and stars that preceded you. You are not just breathing air, you are exchanging atoms with the global atmosphere in a cycle that connects you to every life form that has ever breathed. You are not just seeing the world around you, you are processing photons of light through incredibly complex biological structures that have evolved over hundreds of millions of years to transform electromagnetic information into conscious experience. And there is something deeply humbling and simultaneously empowering about this perspective. Humbling because it dissolves any illusion that we are special in cosmic terms. We are made of the same substances as everything else in the universe. We follow the same physical laws that govern stars and galaxies. Our existence depends on cosmic processes that began billions of years before any humans existed, and will continue billions of years after our species disappears. But it is also empowering because it reveals that we are an integral part of this extraordinary universe. We are not separate from nature. We are not outside observers. We are nature that has gained capacity to behold, the cosmos studying itself, atoms beholding atoms, and through this contemplation and understanding, through science, we can trace our lineage to the earliest moments of time. We can understand how stars were born and died so that elements necessary for life could exist. We can appreciate the absurd luck and specific historical contingencies that allowed a rocky planet in a habitable zone around an ordinary star to develop stable oceans and atmosphere where life could arise and evolve for billions of years until it produced creatures that could ask questions about its own origin. Neil deGrasse Tyson often emphasizes that understanding our cosmic origins should give us a different perspective on the divisions and conflicts that characterize so much of human history. Because when you truly internalize that all human beings are literally made of the same cosmic material, that there is no fundamental difference in terms of origin between any person, regardless of where they were born or what culture they belong to, that we all share a common evolutionary family tree dating back to the first organisms on the early Earth, and that we are all temporarily using atoms that have existed in countless other forms before us, and will exist in countless other forms after us, this should cultivate a sense of fundamental connection between all humanity and, furthermore, between all life. We are all temporary part of a great cosmic recycling of matter, differing only in how these atoms are temporarily organized, not in their fundamental essence. And this perspective also offers an interesting answer to the question of the purpose and meaning of life. Because, if you hope to find some cosmic purpose imposed from outside, some ultimate reason programmed into the universe for your existence, science honestly offers no evidence for that. The universe doesn't seem to have been designed with you in mind. Stars don't explode to create heavy elements because they want to make life possible. They simply follow the laws of nuclear physics. Planets don't form to host life. They form because gravity causes clouds of gas and dust to collapse. Evolution was not intended creating conscious humans. It simply selects variations that best reproduce in specific environments. But recognizing that there is no externally imposed purpose does not mean that there is no purpose at all. Because you are a complex system capable of creating your own values and meanings, you can choose what matters to you. You can decide what you want to do with the few years you have, using this temporary configuration of stellar atoms that we call the human body. If this video expanded your understanding of the deep origins of your existence, leave a like, subscribe to the channel, and turn on notifications because we have many more fascinating scientific explorations about the cosmos, physics, and the mysteries that still remain to be unraveled. Each video is a new journey through human knowledge about the universe we inhabit. And when you really consider all the contingencies that had to line up perfectly for you to exist, the probability becomes almost inconceivably small. The universe had to have the right physical constants to allow formation of stable atoms. If the strong nuclear force had been slightly different, carbon could not have formed. If the cosmological constant had been very different, the universe would have collapsed back or expanded too quickly to form stars. Specific stars had to live and die by spreading heavy elements into the specific region of space that eventually became our solar system. The sun had to form with the right mass, not too big to burn too quickly, not too small to not provide enough energy. The Earth had to form at the right distance from the sun, not too close to be too hot, not too far to be too cold. It had to have enough mass to retain an atmosphere, but not so much that it retained too much hydrogen and helium, making it a gas giant. It had to have a large moon to stabilize its axis of rotation. Maintaining a relatively stable climate over billions of years, it had to have a strong magnetic field generated by its metallic core liquid to deflect harmful solar radiation. Oceans had to form and remain liquid for billions of years. Life had to emerge, survive through several mass extinctions, evolve multicellular complexity, develop oxygenic photosynthesis to transform the atmosphere, survive at least 5 major mass extinctions that wiped out most species. And after complex multicellular life arose, our specific ancestors had to survive and reproduce through hundreds of millions of years, through the transition from ocean to land, through the age of the dinosaurs, through the extinction that killed the dinosaurs but spared our mammalian ancestors, through the evolution of primates, through hominids, until finally reaching modern humans approximately 300,000 years ago. And even then, their specific ancestors had to survive diseases, predators, famine, wars, natural disasters, through thousands of generations until their parents, specific people, met and decided to have you. And among millions of sperm, the specific one that carried half of your genetic material had to be the one that fertilized the specific egg that carried the other half. Any difference at any point in this incomprehensibly long chain of contingencies, and you would not exist. Maybe someone else would exist. But no, you with your specific genetic makeup, your specific experiences, your specific consciousness. So yes, the answer to the question of where you really came from is simultaneously humbling and inspiring. You came from a chain of cosmic, geological, chemical, and biological events that spans almost 14 billion years. You are made of stardust. Literally, the heavy atoms in you were forged in stars that lived and died long before the sun existed. You are part of an unbroken evolutionary lineage that dates back to the first molecular replicators in Earth's primeval oceans, nearly 4 billion years. You are an incredibly unlikely temporary configuration of ancient matter that has gained the ability to think about itself. You are part of the cosmic puzzle, a small but integral piece in the vast tapestry of matter and energy that makes up our universe, and perhaps most extraordinary of all, You are able to understand and appreciate this story, to trace its lineage through time to the Big Bang, to marvel at the epic journey your atoms took through stars and interstellar space until they eventually organized themselves into the form you are reading or hearing these words now, and this ability to understand and wonder is in itself one of the most extraordinary phenomena in the known universe.